Today we're going to make the transition from simple harmonic motion, which we said is motion in which the restoring force is proportional to the displacement. In other words, motion that repeats itself, back and forth motion, to and fro motion, to waves. Waves are these things that carry energy from one place to the other, like a water wave. A water wave carries energy from one place to the other. You jump into the side of a swimming pool, the edge of a swimming pool, and the person floating on the air mattress on the other side of the pool eventually starts bobbing up and down, moving up and down, because your energy was transferred to them. What does simple harmonic motion and waves, what do those two things have to do with each other? Why are we looking at simple harmonic motion one day and then waves the next day? Well, ultimately, it's because waves really are just a whole bunch of examples of simple harmonic motion. Waves consist of the simple harmonic motion of individual particles within that wave. I'm going to show you a little demonstration here to illustrate for you how exactly that's the case. How exactly simple harmonic motion of individual particles causes energy to transfer from the edge of the swimming pool to the other side of the swimming pool where you're just minding your own business lying on the air mattress. So we're defining these waves as a means of carrying energy from one place to the other. Okay, in the demonstration that we just did, I sent a wave pulse down from my hand. The energy was transferred to Haley's hand. You saw Haley's hand move. She said she felt that. The energy was transferred. But we didn't transfer any particles. I didn't throw a slinky at her. Okay, I didn't go and give her a high five. She felt the energy from my hand by the wave transferring that energy. Now, how did the wave transfer that energy? Well, you saw the little piece of masking tape in the middle of the slinky. It was going back and forth, back and forth, back and forth. We define motion that goes back and forth, back and forth, back and forth as simple harmonic motion. So really, this wave is just a whole bunch of different simple harmonic motions taking place at the same time. The simple harmonic motion of the first particle causes the simple harmonic motion of the second particle, which causes the simple harmonic motion of the third particle, and so on, which ends up giving us this wave that we saw in the slinky and transferring the energy from one end to the other. Now, we also showed you in the demonstration these two types of waves. We have the transverse wave, and we have the longitudinal wave. The transverse wave is the wave that we typically think of as being the wave. It's the wave in which the particles of the wave vibrate perpendicular to the way the wave is traveling. So this is the motion of the particles, the simple harmonic motion of the particles. Meanwhile, the wave is traveling this way. A longitudinal or a longitudinal wave, on the other hand, is a wave in which we have this area of higher density. Okay, when I sent a longitudinal wave down the slinky, you saw that the particles in the slinky were closer together in some spots than others. In other words, you get this area of compressions of the material, the slinky in the case of the demonstration. And then this area of extension, and then compression again. And then extension, and then compression again, and so on. The particles within this longitudinal wave are going back and forth this way. The wave itself is going along the same axis. So if the particles are moving perpendicular to the wave, as you saw in the demonstration, that's a transverse wave. And that's most of the waves that we see. A longitudinal wave, on the other hand, still transfers energy via the simple harmonic motion of individual particles, but it does it in a different way, in that the particles vibrate parallel to the way the wave is traveling itself. Yep. Simple harmonic motion, SHM. That's a good question. It's kind of hard to see that, isn't it? Let's look at what kind of wave is this again? transverse. Let's look at the transverse wave in a little bit more detail here. Okay, we got a graph plotted of a transverse wave. This graph is y versus x. So the y position versus the x position. The y-axis, okay, the vertical height of the wave versus the horizontal position of the wave. Let's say the wave is traveling this way. Okay, the velocity of the wave is, let's say, to the right. We've got a few things labeled here. First of all, the particle motion. We've already established that if the wave is moving to the right, the particles will vibrate up and down, perpendicular, in the case of a transverse wave, to the direction of motion. The simple harmonic motion of the particles is given to you right there. Now let's define a couple parts. The crest and the trough. The crest of a wave is that bump on a wave, the top of a wave. When I was growing up in rural Nova Scotia, about your age, getting my driver's license, although, how old are you guys? 16, most of you? Some of you 15? We couldn't even get a learner's permit until I was 15, until we were 16, as opposed to 14 where it is here. But I remember we had the same thing as you guys. When you do your learner's permit, you have to study all these signs and whatever. And some of the signs are a little bit different depending upon where you go. Like a stop sign is a stop sign no matter where you go, right? But there's certain signs that are a little bit different depending upon the province or country or whatever that you're in. I remember one of the signs that you'd often see in rural Nova Scotia, not only in the little driver's handbook that you had to study, but in real life. You'd be driving up this hill, and there would be a sign that would say blind crest. And what that meant was that you couldn't see over the top of the hill. There could be a driveway or another road coming out onto the highway on the other side of the hill, but you weren't going to see it. So they're warning you that, look, be careful. Maybe you should slow down here because you can't see over the top of this hill. The crest of the hill was the top of the hill. It's kind of like you driving up like this. You're driving up the hill. There's a driveway right here. Somebody in a pickup truck might be pulling out onto the highway. You don't see them until the very end because this is a blind crest. The top of the hill, the top of the wave is the crest of a wave. Now we could label it there. We could also label it there. Okay, the crest of the wave is any top of the wave or bump on the wave or peak of the wave. They all should be the same. Now what's a trough? Well, the trough is the dip in the wave, the bottom of the wave. It's like a feeding trough, like pigs eat out of a trough, right? When you visualize that trough from the end, you see it as this dip like this. Okay, this is the trough of a wave, the trough of a wave. The bottom of the wave. So the crest of the wave is the top of the wave, the trough is the bottom of the wave. Now, here's a brand new one for you. A brand new variable for you. Never seen this one before, I guarantee it. This isn't even English, for heaven's sake. Lots of times in physics, we use Greek letters. Mu is a Greek letter, right? Coefficient of friction. Mu is a Greek letter. Lambda is also a Greek letter. It's like an upside down Y. Lambda. Okay, that's the Greek letter. Now, what does this Greek letter wavelength, what does this Greek letter lambda mean or represent? It's the wavelength of a wave. It's the distance over which the wave repeats itself. So that could be the distance between a crest and a crest because the wave repeats itself over that distance. It could be the distance between a trough and a trough. Or it could be the distance between this spot and, tell me when I reach a wavelength. Say stop when I reach a complete wavelength here, a complete cycle of a wave. Okay, tell me when to stop. Oh, you guys got that so wrong. That's one wavelength, right? That's the distance over which, how did you miss that? That's the distance over which a wave repeats itself. Or, you know what, it could be from here to here. Be careful, though, you don't go a half a cycle. Okay, be careful you don't go from, let's say, here to here. That's not the distance over which the wave repeats itself. You're not starting over again there. Okay, you're starting over again here. Okay, same deal down here. Okay, temptation is, okay, you're right here. Oh, well, it repeats itself here. No, it doesn't. It repeats itself here. No, it doesn't. It repeats itself here. That's where it starts repeating itself to be the same thing as where you started before. The distance over which the wave repeats itself is lambda, which is that Greek letter that looks like an upside down lowercase y. And finally, amplitude. Amplitude is given by the symbol A. It's the size of the wave, the height of the wave. And it's related to energy. Be careful when we're talking about the height of the wave, though. The height of the wave relative to what? Well, the amplitude is always measured from this little line here, the x-axis. We call that the equilibrium position, the natural position. If this is a water wave and the water is calm, okay, that line that's the x-axis would be that calm water. It's measured from the calm point, from the equilibrium position to the top of a crest. Or, for that matter, you could measure it from the equilibrium position to the bottom of a trough. It would be the same value. As long as this wave was consistent, it would be the same value. Go ahead. The height of the crest will always be the same as the trough as long as the source remains the same. So what caused this little trough? Well, some disturbance. What caused this crest and this trough and this crest? Some disturbance. As long as the disturbance was the same, then yes, the height will always remain the same. If you happen to have, let's say you're causing this wave by dipping your hand into the water, constantly dipping your hand into the water, crest, trough, just like that. But if you all of a sudden, partway through, start punching the water instead of just dipping your hand, well, then the amplitude of the waves at that point will start becoming bigger. So in that point, you won't have all the amplitudes the same, right? But as long as the source is constant, then the amplitude of the wave will be constant. Yep. Okay. Here's the other kind of wave. This isn't a very good diagram, but it's the best I could do with Microsoft Word. This is what we call not a transverse, but a longitudinal wave. In a longitudinal wave, you get these areas of compressions where the particles in the wave are closer together. In these areas, we call them rarefactions, where the particles of the wave are spread out. They're further apart. Compressions, rarefaction, compression, rarefaction. Continues that cycle, compression, rarefaction. The wave is moving, in this case, to the right, but notice the direction of the particles. It's to the right and left. So in the last case, the particles are moving perpendicular to the wave. In this case, the particles are moving in simple harmonic motion, parallel to the direction of the wave. A compression we'll just define as an area of, how do we want to say this? An area of high density, or an area where the particles of the wave are closer together. And a rarefaction is an area of a wave where particles are spread out or further apart. Let's deal with a tiny little bit of mathematics here. When we analyze the speed of a wave, the first thing that we recognize is that the wave itself is traveling, but the particles within the wave aren't traveling. So again, we get those particles within the wave that are either traveling perpendicular to the wave motion or parallel to the wave motion, but they're not going along the wave. When I held the slinky in my hand, Haley held the other end of the slinky in her hand, the particles that I was holding on to didn't physically go from me to Haley. The energy went from me to Haley. So when we're describing this, the speed of the wave, we're describing the speed at which the energy is transferred, not the particles themselves. And we can assume that that energy is traveling at a constant speed. Therefore, we can analyze the speed not of the particles, but of the energy by the equation V is equal to delta D over delta T. The very first equation we learned in Physics 20 describes constant velocity. It's our group A equation, right? Now, we're going to change this equation around a little bit. Make it look a little bit different than we did on our first day of Physics 20. The distance over which the wave repeats itself, the distance over which the wave repeats itself is going to be the wavelength. So we're going to replace distance with lambda. That's legitimate. Okay, lambda is a distance. It's just a very specific distance, the distance over which the wave repeats itself. Now, that's okay to make that substitution, lambda for d, the distance over which the wave repeats itself, as long as I make a substitution for t. If I have the distance over which the wave repeats itself, then I want the time over which the wave repeats itself. Now, I haven't told you about this variable, at least not in this context. Does anybody think they might know what the time in which the wave repeats itself is known as? The period, big T. So the distance over which the wave repeats itself, the time over which the wave repeats itself. So V is equal to lambda over T. Now, that's a perfectly valid equation that you can use to solve these problems. Having said that, it doesn't appear on our data sheet. This one does, under kinematics. This one doesn't appear. We know, however, that T, in the context of circular motion and simple harmonic motion, and really we're just dealing with simple harmonic motion here, right, of a whole bunch of particles, T is related to frequency by this equation. T is equal to 1 over F. So I can sub in 1 over F for T. Now, we don't need to do that, but if we want to get the equation that appears on our data sheet, we do. T is equal to lambda over 1 over F. Now, that's kind of ugly looking, so let's simplify that a little bit. Lambda over 1 over F becomes the same thing as saying lambda times F over 1. Right? Divide by a fraction, multiply by the reciprocal. That gives us an equation that does appear on our data sheet. V is equal to F times lambda. V equals F lambda is the same equation as this. They just look differently because we're using terms that are specific to waves, not general to any object moving at a constant speed. So the speed of the wave is equal to the frequency of the wave times the wavelength of the wave. Now, these variables affect each other, right? Well, V and lambda do. Remember this. This becomes important later on. The frequency of the wave, which is the number of waves per second, right? This is a low frequency wave. This would be a high frequency wave. More waves per second. The frequency of the wave never changes. Once the wave has been made, it always stays the same. The speed can change. Okay, when you go from deep water to shallow water, the speed of the wave changes. If light goes from air to glass, the speed of the light changes. The speed of the light or the wave can change, as can the wavelength. But once the wave has been made, the frequency, the number of waves per second that you have, never changes. It'll always stay the same. All right? Trust me on that for now, and you'll see when that really matters a little bit later on. Here's a question that's not that unlike, Bart, the question on that assignment. To generate waves in a stretched spring, you're going to oscillate. What does the word oscillate mean? Yeah, it moves back and forth. So basically, when you've got oscillatory motion, it's back and forth motion, which we don't call oscillatory motion. We call that simple harmonic motion. Same thing, right? Oscillates back and forth. Simple harmonic motion back and forth. at a frequency of 2 hertz. The speed of the waves is 5.4. What's the wavelength? Well, let's write down our givens here. 2.00 hertz for our frequency. Our speed is 5.40 meters per second, and we're looking for lambda. On our data sheet, we see the equation V is equal to F times lambda, which we just derived, but also appears on our data sheet. Rearrange it to solve for lambda. Take the F over by dividing, it becomes V over F. 5.40 meters per second divided by 2.00 hertz gives us a wavelength, or a distance from one crest to the next, or one trough to the next trough, of 2.70 meters. Let's take a look at these 3 questions on page 409. Let's take a look at number 2 here, everyone. A submarine sonar system sends a burst of sound with a frequency of 325 hertz. The sound wave bounces off an underwater rock face and returns to the submarine in 8.5 seconds. The wavelength of the sound is 4.71. How far away is the rock face? That's essentially how bats see, right? They sound this sound wave, this ultrasonic wave, it bounces off of something, and then the bat detects it, measures how far away the object is almost instantly by how long it took that wave to come back. Submarines can't necessarily see underwater, right? They can't see where they're going, so they have to have a way of seeing, and they have this way of seeing by bouncing sound waves off these sonar waves. All right, we got a frequency here of 325 hertz. I think that one's pretty clear. The wave bounces off a rock and returns to the submarine 8.5 seconds later. The wavelength is 4.71 meters. Okay, lambda. We've got a time here of 8.5 seconds, right? And we want to find the distance, how far away the rock face is. Well, we're looking for D. The only option that I can think of is to say V is equal to delta D over delta T. But I don't know what V is. So I'm going to solve for V using V is equal to F times lambda. V is 325 hertz times 4.71. What do we end up getting when we multiply those 2 numbers together? Someone's got to have that. Yep. 1,530.75 meters per second. Now, that's pretty fast. Speed of sound in air, depending upon the temperature, the air pressure, is about 340 meters per second. So this is 4 to 5 times faster than the speed of sound in air. Sound travels faster in water than it does in air, because water is more dense. The particles are closer together. It's easier to transfer the energy through water than it is through air because of the density. So we got the speed of sound now. Let's plug that in and solve for D. If we rearrange that, we get V times T. The speed is 1,530.75 meters per second. And we multiply that by the time of 8.50 seconds. When we do that, I think we're going to end up getting about 13.2 kilometers, or 13,200 meters. Is that right? What's the exact number there? 13,000 and 13,011 meters. But wait a sec. When we look at the answer here, it says 6.51 kilometers. Not even close. This is 13 kilometers. They say the answer is 6.5 kilometers? What's up here? Have we done something wrong, or have they done something wrong? Yep. Okay. So Earl is saying we're supposed to use half the time. Why are we using half the time? Yep. Good. Excellent. Okay, we want to know how far the rock is away. We want to know the distance that the sound travels to the rock. Therefore, we need the time that it takes the sound to go to the rock. We don't have that time. We've got the time that it takes the sound to go to the rock and back. So we're going to divide that time by 2. We can go 4.25 seconds. Don't automatically divide a time by 2. Look at the question. Okay, look at the question and see if you should divide it by 2 or just leave it as is. If we are given the time that it takes to go to the rock, then we wouldn't divide it by 2. If we're given the time that it takes to go there and back, then we do have to divide by 2. Do the math there, and it works out to be 6.51 kilometers, or 6.51 times 10 to the 3 meters. Now, there is one more option here that we could have done to get the correct answer. Instead of dividing the time by 2. Anybody have any ideas for that? We solved for the distance, right? But when we used a time of 8.5 seconds, we got the distance there and back, right? What could we have done there, Jacob? We could have divided the distance by 2, right? So get the distance there and back, and then divide it by 2 to get the distance there. 6.51 times 10 to the 3. All right, and number 3, again, real close to that question that you see on your Wested alternate assignment. Number 3 says a fisherman anchors his dinghy in a lake 250 meters from shore. The dinghy rises and falls 8 times per minute. 8 times per minute. So we're going to say the frequency here is 8 cycles divided by 60 seconds, 1 minute. 8 divided by 60 would be, is that 0.133? Now we get the frequency. Yep. No, 60 seconds divided by the cycles would be the period. Remember, period, 1 second, guys. Period is time per cycle. So you want to find period, time over cycles. Frequency is cycles per time. So it's got to be cycles over time. Let's just finish off this question. Don't back up yet. The time here is 3 minutes, which is 180 seconds, that it takes the wave to go from the dinghy to the shore, and the distance that it covers is 250 meters. We want to know how far apart the wave crests are. In other words, we want to find out what lambda is, how far apart the wave crests are. Let's say v is equal to d over t to get speed. It's 250 meters divided by 180 seconds. Okay, that's going to give us the speed. Not sure what that is. And then we're going to say v is equal to f times lambda to solve for lambda there, given the speed that we just calculated. Does that make sense? Okay, that's it for today, guys.